Good evening, ladies and gentlemen. My name is Cameron Spalding, and today I'm going to talk to you about protein structure. As you can see here, we have a protein written on the wall, and it's mostly made up of alpha helices, which I will talk about later. But right now, I just want to emphasize that if this protein's shape is changed in any way, then the protein's function will also be changed. Oftentimes the function it'll be less functional. It could become non-functional, and on rare occasions, very rare occasions, it can become more functional. The protein shape is key in determining the function of a protein. This is also seen with the contractile proteins, actin and myosin. I'll draw actin and myosin real quickly. A rough sketch at least. Myosin has two heads that act on actin to move the muscle. These two heads attach to actin and pull it in the direction that the muscle contracts. And that's just one example of how a protein's shape determines its function. All proteins are made up of amino acids. There are 20 amino acids in the body, and all proteins have 4 classifications to their structure. The first is primary, secondary, tertiary, and then last there's quaternary. Proteins are arguably the most important molecule in the body. They function not only with contractile proteins, but enzymes as well that help speed up different chemical reactions. Right now I'll just draw a simple amino acid on the chalk wall here. Okay. Okay. All amino acids have this amino group, a hydrogen, and this carboxyl group attached to a central carbon. The only difference in all 20 of them is this R group. And primary structure is the one we'll talk about first. Primary structure is basically just the sequence of amino acids, like the linear sequence. So we can have sample amino acid, amino acid, amino acid, amino acid, and that can continue for as long as the polypeptide chain is. Each amino acid is connected via a peptide bond, and once you get a long chain of amino acids, it becomes a polypeptide. But these peptide bonds, they're very strong covalent bonds, which means that they share electrons, and there will be an amino group on one end, and the amino group of the next amino acid will covalently bond with the carboxyl group of the previous amino acid. These covalent bonds have a very high bond dissociation energy, which means that it's very difficult to break that bond. But next we have secondary structure. And secondary structure, there's 3 types. There's alpha helices, there's beta pleated sheets, and then there's random coils. These secondary structures are when these polypeptides they basically fold on themselves um, it's helpful to think of each amino acid as a letter, and then a polypeptide becoming a word, and then when the words combine to form the secondary structure, then you can think of that as a sentence. But these secondary structures are formed when the like parts of amino acids, which the carboxyl group here and the amino group here, they will either attract or repel one another, and that's what will cause these coils that can be right-handed or left-handed coils, or beta pleated sheets, which looks something like this. This is a very, very rough sketch, but it's basically sheets on top of sheets of amino acids. And the bonds that hold these together are non-covalent bonds, such as hydrogen bonding, and they're bonds that have very weak dissociation bond energies, which means they're a lot easier to break. So next we have tertiary structure, and this is a prime example of tertiary structure. It's basically where the secondary structure, which is usually alpha helices, fold in on themselves and create this kind of globular mess. The bonds seen here are non-specific hydrophobic interactions, and these are also, they can be relatively weak and they can also be relatively strong. They have hydrogen bonds, which are also seen in the secondary structures, but there can also be disulfide bonds, which are relatively strong, and there can also be salt bridges, and it would take addition of heat or acid to break those bonds. As in secondary structure, we had the attraction and repulsion of the like parts of the amino acid. With tertiary structures, we have attraction and repulsion of the different R groups of the amino acid. This can be due to different charges or different attractions to certain elements. But yeah, so that's tertiary. And quaternary structure is basically when more than one polypeptide tertiary structure comes together to form a protein. And a good example of a quaternary structure would be hemoglobin, which is a tetramer. So it's made up of 4 polypeptide units. You can also have a dimer and a trimer, which are 2 and 3 polypeptide units respectively. But yeah, so hemoglobin is the protein in the blood that carries oxygen, and it's basically the bonds of a quaternary structure are also seen in the tertiary structures as well. You have disulfide bonds and salt bridges, things like that, which have a low to medium bond dissociation energy. So it'll take some heat or addition of acid to break those bonds. So those are basically the elements of the 4 classifications of the structure of proteins. Heating causes the denaturation of proteins. Denaturation is basically the loss of the quaternary, the tertiary, and the secondary structures. So basically, if we were to put this protein in heat, it would unfold and get rid of the tertiary structure, be left with the secondary structure. It would break those disulfide salt bridges, those non-specific hydrophobic bonds. Um, then the secondary structure, the hydrogen bonds, would also be broken after excessive amounts of heat. But this here, the primary structure of the protein, usually doesn't break down unless the heat is just extremely excessive, and also the possibility of addition of acid. So it's this primary structure, these covalent bonds, hold the protein, the polypeptide together. It's possible once you take away that heat for the protein to reform, as long as any part of the amino acid didn't get damaged. But yeah, so it's the primary structure that is the determines the function of the protein. For that reason, the strong bond dissociation energy of the covalent bonds seen within the primary structure. My name is Cameron, and this has been a short lesson on the 4 classifications of the structure of the protein, and thank you for your time.